Logic is the language of mathematics. It's really the thing that's underlying everything that we do, and it'll be the backbone of all of the proofs that we write throughout this semester. So I can't stress enough that it's important to understand these underlying concepts now, so that when we start putting some mathematical structures to them, the underlying logic feels good to you still. You can fall back on it as a tool rather than like some kind of stumbling block. So the first idea that we have is this idea that we have statements. So this whole idea of statements is going to feel a little bit like a trip down the grammar lane, but it's okay. I am not great at grammar either. You'll be all right. So in math, statements are what we want. The statement's a declarative sentence or an assertion that something's true or false. It can't be both. Anything that can be both true and false is not a declarative sentence, it's not a statement. So statements, they're all about the truth of something. So the integer 91 is prime. That's either true or false, right? It can't be both. It's not possible to be prime and not prime at the same time. So that's an example of what we're talking about when we're talking about statements. So whether or not you know what a declarative sentence is, it's fine. Just think to yourself, is that statement always true or always false? Like, is there a possibility of it ever being both at the same time? Because if there is, then it's not a statement. So we care that these statements have a truth value and that they're true or false. And every statement's going to have this truth value. And the truth value is going to be very important when we start thinking about logically how different things can link together. A lot of times statements, we use letters P, Q, and R, and we'll use subscripts even. P is really the go-to for statements. So in this example that they give you really quick, they give you a statement P being the number pi is greater than 3.14 but less than 3.15, and R, the integer 0, is an even integer, and both of those are true statements, so they both have truth value true. So whenever you're asked what the truth value of a statement is, your answer should be true or false. And 91 is not a prime integer, and so the truth value of Q, that statement, is false. So this is where the trip down grammar lane feels even more grammary. There are sentences that are imperative, so they're the things that tell you to do something. So whenever you say, like, solve the equation, that's not a statement. So sentences that are interrogative, so questions, all right? Like when I ask you what is the truth value, that's also not a statement. Or anything that's exclamatory, so things that make sense to have an exclamation point after them for the most part. So this problem is unfair. That's a statement. And it kind of gives an opinion. So it could be true and false at the same time. Those things are not statements, all right? So declarative statement is one that we know is true or false. And there's no opinion guessing game to be played. So one of the things that can happen is sometimes we want a statement where we can plug in different values for it. And those different values might change the truth value as we go. So an open sentence is a declarative sentence that contains one or more variables, and each variable represents a value in some prescribed set, which we call the domain of the variable, and which becomes a statement when we put values in for those variables. So we might write these as P of X, Q of X, or R of X. Again, P of X is the default go-to, and X here is our variable. So just a quick bit about wordings and vocabulary. Whenever P of X is an open sentence where the domain is S, then we say P of X is an open sentence over the domain S. So an example of this playing out would be having a variable that's coming out of one of the sets of numbers, like the set of integers. So here I have an open sentence P of X over the domain of the integers. And my open statement or open sentence is 5x squared plus 8 equals 53. So we can solve for x here, and we know that this is a true statement whenever x is 3 or negative 3, and it's a false statement otherwise. So for some values of the variable, it's true, and others, it's false. So here's an example playing out. We have an open sentence with two variables, x and y. So we have p of xy. The absolute value, x minus 1, plus the absolute value of y minus 2 equal to 3. So we take the domain of these variables. So we have x is in the set 3, 2, 1, and y is in the set 1, 3. So we notice that if we plug in 3 for both variables, which is legal because 3 is in both domains, we get a true statement. So we have our open sentence, p of xy, is a true statement if x and y are 3 and 3. And the same thing is true if we plug in 3 and 1, which is again allowed because those values fall in the respective domains. And it's a false statement if we choose any other pair. So open sentences, again, you'll be able to determine values of the variable where they might be true or where they are true statements, and you'll have values of the variables where they'll be false statements. So the final thing for statements is this idea of a truth table. If I have a single statement P, it can be either true or false. The same thing for a single statement Q. It can either be true or false. However, as soon as I put P and Q both together, I have 4 possible pairings. So I can have true and false, false and true, or false and false. This is the same as if you're flipping a coin and you're saying how many different combinations of heads and tails can I get between 2 coins where I can distinguish between the coins. So you've probably done that at some point. This is the same idea playing out. So adding a third statement R into that, I go from having 4 possible combinations to having 8 possible combinations, because R can be true with all 4 or false with all 4, and all of them are different statements. So that's all that a truth table is when all we have is statements. And we're going to build these truth tables up, and they are going to be a huge friend of yours. So make sure that you have it down pretty quickly, can list out all of the possible pairings of truth values for statements when you have 1, 2, or 3 different statements that you're working with. This is going to be a good tool for you going forward. So negations is the simplest thing that we can do to a statement, and it is exactly what it sounds like we're going to do. We're going to take a statement and we're going to say, not that. So I have a statement P, and I'm going to make the statement not P, and that is the negation of P. So we show it by putting a little tilde out in front of the P. That's the notation that we'll use. So there's some examples there of what that might look like for some statements Q and R there. Really, it's always adding the word not to the verb though. Right? So the negation of a true statement is always going to be false. If I tell you that my name is Kayla, that's true. And if I say my name is not Kayla, it's false. You can't have a statement that has a definitive truth value and then add the word not to the verb and it now all of a sudden not have the opposite truth value. So the negation is always going to have the opposite truth value of the original. So here's a truth table, again with the single statement P being true or false, and now we've added a column for the negation of P. And notice, whenever P is true, not P, the negation of P is going to be false, and whenever P is false, the negation of P will be true. Disjunctions are stepping up the level of complexity just a little bit with this. So in a disjunction, you're going to take 2 statements and you're going to put them together with the word or you're going to use a thing that looks like a V as a symbol in between the 2. So the disjunction is true if at least one of the things is true. And this sounds right in the English language too. If I say that my name is Kayla or my name is Megan, one of those things is true, so the whole thing is true. And it doesn't really matter what this other statement is as long as one of them is true. if they are both false. So if I said, my name is Frankie, or my name is Megan, both of those are false. So the entire statement is false. So the only way that a disjunction is false is if both statements are false. So we can take a truth table where I have a statement P and a statement Q, and I'm taking the disjunction of them. So I'm saying P or Q is true. So anytime P is true, the disjunction is true. And anytime Q is true, the disjunction is also true. The only time that the disjunction comes up false is whenever both P and Q are false. So that's my truth table for a disjunction. And finally, a conjunction is when I take two statements and I join them together with an and, or a thing that looks like an A without the crossbar in it. Mountaintop. All right, so I'm bringing two things together as a conjunction. So this is true only when both of them are true. And this again follows pretty closely from English. If I say my name is Kayla and my name is Megan, one of those things is false. So the whole thing is false. All right. Again, we take our truth table and we look and we see the only time that our conjunction column is true is when both of our statements, P and Q, are true as well. And every other time it's false because either P is false or Q is false. And as long as one of them is false, the conjunction will be false. So those are our basic statements and some really basic things that we can do with them.